Alright, so we're going to take a step back from some of Manim animations. I hope you guys checked out those videos. Those are styles of videos that I'm trying to work towards while keeping this style of videos where I do the handwritten stuff. And it takes quite a long time actually. And so I'm going to try to work on those videos, which will come out like once or twice a week, and then try to produce new topics, new math concepts and problems and stuff like that as more often, of course, maybe like 4 times a week. So today we're going to talk about implicit differentiation. So suppose you have a equation like the one that I have right here, and if you know what this looks like, it's going to be a circle with radius of 5, centered at 0, 0. So actually, let's just do this. So yeah, it's a pretty terrible circle actually, so I'm going to redraw this. Something like that, okay? You guys get the gist of, what this is. This is, Jesus Christ, it's so bad. Okay, there we go. So it's a circle. And we're asked to find the derivative of this at any given point. We're going to find what dy and dx is. And this is why the derivative notation is actually kind of important, because you're taking a derivative with respect to x this time. And the question is like, okay, well, what is the slope of tangent at this point? What's the slope at this point? How can we generalize these slopes of tangents into a function? And for regular curves, and this isn't really a function, by the way, it's not a function, obviously, but for functions, you had smooth curves, and then you knew they were differentiable. You found the derivative using the rules. Well, the rules are still going to apply, but there's just one more thing that we're going to need to add. So let's take our x squared plus y squared is equal to 25. And we're going to take the derivative of each side of the equation. Now, this right-hand side is just going to be 0. Once you take the derivative, and I could even say take the derivative here as the signal, the right side is 0, obviously, right? Because a constant's derivative is going to be just 0. For x squared, it's going to be the same as always. The same as always. So we're going to have 2x, just using power rule. So after using the power rule for that, we're going to use the same rule for y squared. So it's going to be 2y. But that's not it. We took the derivative of y, but we took the derivative with respect to x. This isn't an x term. So anytime that you're taking a derivative, with respect to a different variable, you need to tag on the dy dx. Okay? And that's really important. You can think of it as, like anytime you have a y, any derivative you take, just multiply a dy dx. And trust me, it'll keep things, that's the simplest way you can go about this. And all you have to do from here is now solve for dy dx. So we're going to have our 2x is equal to negative 2y dy dx. And simply, if we solve for dy dx, it's going to be 2x over negative 2y, which is the same thing, and I'm going to lower my microphone here. It's the same thing as just negative x over y. And this is now we have our derivative, dy dx, and it's containing both x and y. And that's really important here. So why is that important is because this isn't a function. It takes inputs of x and y values, and they both matter in a sense. You would think about it like that. So when you find the derivative, we're going to need to take inputs of both x, like let's say this was like 3 comma 4, we need to plug in the 3 and the 4 now. So you need two variable knowns to find the slope of the tangent, but this generalizes it, and that's what we're looking for. And that's what implicit differentiation is all about. Okay, so take the same idea, let's say you have the derivative of x cubed e to the y is equal to 1025. Well, this right side is just going to be 0 as always. So take a derivative, the right side turns to 0, and I'm going to actually move it to the left here and move this to the right. And so 0 is equal to, now we need to apply the product rule, okay? So derivative of first times the second. So 3x squared e to the y. Now we don't need to multiply a dy dx to this part because we chose the first thing to differentiate as x cubed, and that's in the x world, so it's okay. Plus, now it's going to be x cubed, but now we have to take a derivative of the second function, which is just going to be e to the y. But here, we took the derivative of something with a y. So now we need to tag on a dy dx. Okay? And that's really the gist of it, guys. From here, it's just going to be simple solving. So we're going to solve for dy dx now. So we now have negative 3x squared e to the y is x cubed e to the y dy dx. And from here, dy dx is just going to be negative 3x squared e to the y over x cubed e to the y. Simplify this further, this will just be negative 3 over x. And there's our solution. Okay, let's do another problem now. Say I had the equation, say it's like 200 is equal to y squared over e to the x. Okay, or actually let's do something else. Let's do ln of x. How are we going to approach this? Well, now we're going to use the quotient rule, and we're going to take a derivative here. So left hand side is 0 as always. Constant's going to go to 0. We have the derivative of the top, which is 2y times ln x. But remember, we took a derivative with respect to x. And so that's, when we say dy dx, we're saying take the derivative with respect to. The denominator indicates what variable you're taking a derivative with respect to. Because if I asked you x squared and find the derivative with respect to w, well, in this world, x squared is actually a constant, so it doesn't matter. So that notation really matters, guys. So 2y ln x times dy dx minus y squared over x, right? Derivative of ln x is 1 over x, multiply that to y squared, and all of that over ln of x squared. And yes, I will do that notation. Okay, so how are we going to simplify this? Well, we can do some manipulations here. So the first thing is we can add this term to the right side. So it's going to be y squared over x over ln of x squared is equal to 2y ln x dy dx over ln squared x. And we're just going to completely ignore the ln squared x terms. So y squared over x is 2y ln x dy dx. And from here it's just, simple arrangements. It's going to be equal to y squared over 2y ln x times x. And just to simplify this even further, it's going to be y over 2x ln x as our solution. So really easy, right? Just tag on a dy dx. Now let's go back to that same problem. X squared plus y squared equals 25. Now I'm going to ask you to take this derivative with respect to y. So the question is going to be like, find dx dy. Okay, so now when I take the derivative of x squared, I need to tag on a dx dy. So that is why notation is extremely important. It's asking us to take a derivative with respect to y. And so now this changes everything. And of course, this is just going to be dx dy is equal to negative y over x. Really important. Now, what else can, obviously you guys get the gist of the idea. Anytime you take a derivative, something with a y, just tag on a y prime or dy dx, right? Well, to make this even trickier, we can take it even further. So we know that for the first problem, that dy dx was negative x over y, right? Remember that y, it was x squared plus y squared equals 25. Now I'm going to ask you to find d squared y over dx squared. And this is the notation for the second derivative. Okay, so find the second derivative. Okay, so from here, do the same stuff. So now d squared y over dx squared is going to be, okay, so we need to do the quotient rule. So it's going to be derivative of negative x is negative 1. So it's just going to be negative 1y minus the derivative of y is dy dx. Okay, so it's 1 dy dx. So 1 dy dx times just negative x all over y squared. Okay, and one of the biggest mistakes is that thinking when you do a quotient rule for implicit differentiation that you have to tag on the dy dx for the denominator. You don't. It's only when you're taking a derivative. That's all that matters. Okay, so let's just clean this up a little bit. So negative y plus x dy dx over y squared. And we want, now the problem is going to ask you to, write in terms of x and y. So we can't have this dy dx term, so we need to substitute this back into the formula. So, x, it's going to be negative y, and actually it's going to be, we have dy dx, have this little box here. It's going to be negative y plus x times negative x over y all over y squared. And of course, this is just going to be negative y minus x squared over y all over y squared. And I'm going to leave it here. If they ask you to simplify it to as much as possible, go ahead and simplify that. I'm not going to do that because I am a lazy mathematician, and well, there's a saying that good mathematicians are lazy mathematicians. Okay, so that's all you need to know about implicit differentiation, guys, is that when you're taking, when you're dealing with multivariable stuff like this, which aren't really functions, right? There's a y squared term, so that already kind of causes some trouble. When you're dealing with this stuff, just make sure, anytime, first of all, look at what they're asking. If it's dx dy with respect to y, then you need to find everything that's not y and multiply a dx dy to it. If it's dy dx, then make sure when you're taking a derivative of y to the something or something of y, just tag on that little y prime term, and everything's going to be great, okay? Thank you so much for watching, and I'll see you guys in the next video.